Hello, this is Engineering Statistics and Linear Algebra 18 EC44, Module 5. We are taking up the model question paper, Module 5, question number 9 and 10. So this is question number 9 of the model question paper. So we have here reduced the matrix A to the echelon form U and find the determinant of A using the pivots of A. So A is given, and let us try to see the solution for this. So given A, we need to reduce it into the echelon form. For that, this is already one, so it becomes the pivot, and now these two should be made zeros. To make these two zeros, first to make this zero, we should write R2 minus 2R1 should go into R2. R2 minus 2R1 should go into R2. So that means 2 minus of 2 into 1 will be 0, that goes here. 2 into 2 minus 2 into 2, that is minus 2 goes here. 3 minus 2 into 3, that is minus 3 goes over here. Similarly, this should be made 0. For that, we should write R3 minus 3R1. So that is 3 minus 3 into 1 will be 0. 3 minus 3 into 2, that will be minus 3. 3 minus 3 into 3, that will be minus 6. So once having got this, now this is the pivot, and now this should be made equal to 0. To make this equal to 0, we should multiply the R3 by 2 and then subtract this one R2 multiplied by 3, and that is 2R3 minus 3R2. So 2 into minus 3, that will be minus 6, minus of 3 into minus 2, that will become again minus 6. So minus 6 minus of minus 6 will be 0. Then next, minus 6 into 2, that will be minus 12. Minus of 3 into 3, that will be 3 into minus 3, that will be plus 9. So minus 12 plus 9 will give minus 3. So this gives us the echelon form. And the pivots here are 1, minus 2, and minus 3. So if you multiply these pivots, you'll get the determinant, and that turns out to be 6. Now let us see the part B, or rather 2. By applying row operations to produce an upper triangular matrix U, compute the determinant of A. Both these are same, they are not different. Both these are same. Only the statement is different over here, but both refer to the same thing. So going to the solution again. So we already have one here, so that becomes a pivot. So therefore this and this should be made 0. To make those two 0, we should write here R2 minus 2R1, and that will give 2 minus 2 into 1, that will become 0. 6 minus 2 into 2, that will be 2. 6 minus 2 into 3 will be 0. 1 minus 2 into 0 will be 1. Then this should be made equal to 0. For that, we need to just add R1 and R3 and put it in R3. Minus 1 plus 1 will be 0. 0 plus 2 will be 2. 0 plus 3 will be 3. 3 plus 0 will be 3. Then we have in the fourth row, already a 0 is present, so nothing needs to be done, you just need to reproduce. Now this is the pivot. So now these two should be made 0. To make these two 0, we should write R3 minus R2 should go into R3. 2 minus 2, okay, will be 0. That is why this is 0. Okay, 3 minus 0 will be 3. 3 minus 1 will be 2. Similarly, this minus this, R4 minus R2. 2 minus 2 will be 0. 0 minus 0 will be 0. 7 minus 1 will be 6. So now you have 4 diagonal elements. 1, 2, 3, 4 pivots on the diagonal in the upper echelon form, upper triangular echelon form. So we'll get here 1 into 2 into 3 into 6. And that will give us 36. Then let us check the 9b. Find the eigenvalues and eigenvectors of the matrix A. A is equal to 1, 4, 2, 3. So here, to find the eigenvalues, we will write determinant of A minus lambda I, that is equal to 1 minus lambda 4, 2, 3 minus lambda I. Okay, 1, 4, 2, 3 we had. 1, 4, 2, 3 we had. And now the component minus lambda is added to the diagonal. So now 1 minus lambda into 3 minus lambda minus of 2 into 4, that is 8, is equal to 0. So now we have 3 minus 4 lambda plus lambda square minus 8 is equal to 0. And if you solve that, you'll get lambda square minus 4 lambda minus 5 is equal to 0. So lambda is equal to 5 and lambda equal to minus 1. Two different roots we are going to get by using minus of b plus r minus root of b square minus 4ac by 2. Having found the eigenvalues, lambda 1 and lambda 2, this will be known as lambda 1 and lambda 2. We need to find the eigenvectors. So case 1 is, first for the eigenvalue lambda equal to 5, we need to convert this to the row echelon, to convert this to the row echelon form. We generally write the augmented matrix. Even if you write the matrix, it is sufficient. So you'll get here minus 4, 4, 2, minus 2. So you just need to write 5 in place of lambda. 1 minus 5 will be minus 4, 4, 2, 3 minus of 5 will be minus 2. And that is what we have here. And 0, 0 for the augmented matrix. Even if we don't write this, it is all right. So having done that, now we need to make, R1 is replaced by minus R1 by 4. So we are just dividing this by 4. So minus 4. So we'll get 1 minus 1, 0, 2 minus 2, 0. Having done this, we should reduce this to 0. So for that, R2 minus 2 R1, that will give 0. Again, R2 minus 2 R1, that will give 0. R2 minus 2 R1, that will again give you 0. So from this, you can just write, you need to write here x1, x2. Okay, 1 into x1 minus of 1 into x2, that will give x1 minus x2 equal to 0. And that is x1 is equal to x2. So rather, we should remember that this gives you the pivot variable and this gives you the free variable. X1 is the pivot variable and x2 is the free variable. So the pivot variable should be written in terms of the free variable, x1 equal to x2. So x will be equal to x1, x2, that is in place of x1, x1 is equal to x2 we already got here. So therefore x2, x2, x2 common, 1, 1. So the eigenvector for lambda equal to 5 will be 1, 1. Similarly, case 2, lambda equal to minus 1. So that will give you 2, 4, 2, 4. So you can divide this first row by 2, we'll get 1, 2. And then again to make this 2 as 0, we need to write, to make this 2 as 0, we need to write R2 minus 2R1 goes into R2. So therefore, we'll get 1, 2 here as it is, and this will become 0, 0. So from this, again, if you write 1 into x1 plus 2 into x2 is equal to 0, the equation. So that will give us x1 equal to minus 2x2. So the eigenvector associated with the eigenvalue lambda equal to minus 1 is x equal to x1, x2, x1 is minus 2x2 and x2 as it is. So common x2, minus 2 and 1. So the eigenvector is minus 2, 1. So thus we can find the eigenvalues and eigenvectors. Now let us go to the 9c. Factorize the matrix A into A equal to x omega x inverse using the diagonalization and hence find a cube. So it's not omega, it's lambda. X lambda x inverse using the diagonalization and hence find a cube. So A is given for us. We need to do this. So we have A there. So we need to find again the eigenvalues. So for that we write the determinant of A minus lambda I, that is 1 minus lambda, 2, 0, 3 minus lambda. So this will give us the eigenvalues as this multiplied by this minus of this multiplied by this will give you only these two with their roots as 1 and 3. So now the lambda will be equal to 1, 3 in the diagonal and 0, 0 in the other diagonal. Principal diagonal 1, 3 and in the other diagonal it is 0, 0. So that is the eigenvalue matrix. Lambda is the eigenvalue matrix. Now we need to find the eigenvector and hence the eigenvector matrix, okay, which is X. So eigenvector for lambda 1 equal to 1 will be, so you need to write A minus lambda 1 X, lambda I, A minus lambda 1 I into X, that is 0 to 0 to x1 x2 equal to 0 0, that is 0x1 plus 2x2 is equal to 0, that will give x2 is equal to 0. So x is equal to x1 x2 x1 and x2 is 0. So x1 into 1 and 0. Eigenvector for lambda 2 equal to 3 will be A minus lambda 2 I x is equal to minus 2 to 0 0 x1 x2. So minus 2x1 plus 2x2 is equal to 0. That will give x2 is equal to x1. And that will give, in place of x2, you write x1. So x1 you can take common and you'll get 1 1. So here we are considering as if x2 is x2 is a pivot variable and x1 is a free variable. So having done that, we can find the value of the we have found the lambda, which is the eigenvalue matrix. Then the eigenvector matrix, either S or X, whatever you call it, is we have found it as 1 0 here and 1 1 here. So same thing is written here. And so having found that, we need to find the S inverse. And that will give us 1 minus 1, 0 and 1. 1 minus 1, 0 and 1. So having found S and S inverse, we need to find X lambda X inverse or S lambda S inverse is equal to A, or X inverse AX is equal to lambda, or AX is equal to X lambda. So AX or AS is 1, 2, 0, 3, 1, 0, 1, 1, and that will give 1, 3, 0, 3. Then X lambda is equal to 1, 1, 0, 1, 1, 0, 0, 3, and if you multiply this, you'll get 1, 3, 0, 3. So both these are same. Also, X lambda X inverse, you can write all that. And simplify that, and you'll get the value 1203, which is 8. Then to find the value of AK, A to the power K is equal to S lambda to the power K S inverse, and that will give us A cube is equal to 1011 for S, and the lambda K is 1 cube 0 0 3 cube 1 minus 1 0 1 for X inverse or S inverse. So again multiplying these two, you'll get this. Again multiplying these two, you'll get this. So thus you can find A cube. Then 10A. Factorize the matrix A into A equal to U sigma V transpose using SVD. Given A. Given A, okay, we need to what you call factorize it into this using the SVD. So we should know the definition for SVD. So SVD is any real M cross N matrix can be factored as any real M cross N, any real M cross N matrix A can be factored as A equal to U sigma V transpose, where V is n by n orthogonal matrix whose columns are eigenvectors of A transpose A. We need to find A transpose A. Given A, we need to find A transpose A and find its eigenvectors. And the eigenvectors form a matrix which is orthogonal, and that is what is V. Similarly, we need to find the AA transpose. Having found AA transpose, then we need to find the eigenvectors for AA transpose, and those eigenvectors will form the matrix U, which is M cross N orthogonal matrix. Then sigma is the diagonal matrix, which is M cross N, whose diagonal elements are roots of eigenvalues of A transpose A or A transpose. Either of them you can write. Okay, roots of eigenvalues of A transpose A or A transpose. So we need to find this, right? Find its eigenvalues, find its eigenvectors. We need to find this, find its eigenvalues, find its eigenvectors, right? Then find the value of sigma, which is the diagonal matrix whose diagonal elements are the roots of the eigenvalues of ATA or AAT. Then we need to test this. We need to test this, or we can try to write it in a little different way, similar to whatever we might have done earlier. So it is an elaborate procedure. It is too long also. It takes too much time. In the model question paper, he has just put only 8 marks, but it should definitely carry something like 15 marks. Otherwise, it's not solvable. Okay. So 10B. 1. What is positive definite matrix? mention the methods of testing positive definiteness. So positive definite matrix means pivots should be positive. Positive definite matrix is one where pivots are positive. Test for positive definite is 6b and 6c in the book, page 353 and page 355 are the slides which are P14. That is page 14 here. 6b is this: x transpose Ax greater than 0 for all non-zero real values x. All eigenvalues of A satisfy lambda I greater than 0. All the upper left submatrices AK have positive determinants. All the pivots without row exchanges satisfy dk greater than 0. Similarly, we have here, there is a matrix R with independent columns such that A is equal to RTR. Okay, then it is a positive definite symmetric matrix. So we have to show that this is a positive definite or not. So if we see here, you can try to write this whole thing, right? You can solve it and then find the value here, 5x1 plus 7x2, x1 plus x2 greater than 0. So this will give us 5x1 is equal to minus 7x2 greater than 7x2, minus 7x2. x1 is greater than minus x2. So whether that is true, but that is again very difficult to judge. So what we try to do is the second one, 5 minus lambda, 6, 7 minus lambda. For this, we need to find, that is, we are trying to find the eigenvalues. So eigenvalues will give us 11 square minus lambda square minus 12 lambda minus 1. And that will give you one positive and one negative value. Therefore, this is not positive definite. Also, if you take the determinant of this 5, 6, 6, 7, that itself becomes negative and hence it is not positive definite. Okay, then we have the 10C. So this 10C is the matrix, given matrix S or A, whatever you call it. You need to orthogonalize, find the orthogonal matrix Q that diagonalizes the following symmetric matrix S, okay, or A. So for that, let us see the solution. So S or A is given to us. The process is find eigenvalues, find eigenvectors, normalize the eigenvectors. P is the matrix with and the step 4 is diagonalize. The diagonal matrix is D is equal to P transpose A P. So this is the process we should follow. This should be quite simple. We know how to find eigenvalues. We know how to find eigenvectors. Normalizing just means you need to divide by the length of the what you call eigenvector, and then that will give us the P matrix, which is the normalized eigenvector matrix, and from that P transpose you can find. Then P transpose AP is what we need to find. So to diagonalize a symmetric matrix, say compute PTAP where the columns of P are the normalized eigenvectors of A. Normalized just means whatever eigenvector is there, you need to divide it by the length of the matrix. Okay. Then we go to the second paper, 442. So if you see here, 9A1, 9A2, they are just similar or rather to the 441. So we are not going to do that. So again, 9B is eigenvalue, eigenvectors for A and A inverse. So there is nothing to do there. We need to find the trace. Trace will be the sum of the diagonal values of the what you call eigenvector matrix, eigenvalue matrix. Okay. Diagonalize the matrix A and hence find A to the power 4. Earlier we had find the A cube, now it is A to the power 4. So no difference again. 9C is similar to the 9C of the earlier one. So next, if you see over here, we have this. This we have already solved in the earlier video, so we are not going to do that. Now, next is just to see if ATA is positive definite. So we need to find that whether this is positive definite. So this is again, if you see over here, okay, find ATA, then apply the test for positive definiteness, that is 6B and 6C. If one of them does not satisfy, then that will give us the value of that it is positive, not positive definite. It is not a positive definite matrix. Then 10C is almost similar to 10A of the earlier paper. So this finishes the solution, and we will assume that we have finished this module. Okay, so we'll take up probability and random variables in